In this video, we're going to solve this horizontal pulley problem. So here we have a string connected to the wall, goes around this pulley, and it's connected to mass 1 on the end of the string. And then there is mass 2, which is connected to the pulley. And mass 2 is being pushed towards the right with the force of F. The string has a tension of T, and the masses are here. What is the acceleration of A1 of mass M1? So we have the acceleration of mass 2. So A2 is the acceleration of mass 2, and we want to find what is the acceleration of mass 1. So I want to do kind of a thought experiment here. So imagine that we have this string and connected to this pulley, and then at the end of the string, all the way back here, we have some mass that's over here. And let's assume that this string had a length of 1 meter. So which means that it's half of it is on the top, half of it is on the bottom. The top half would be half a meter, and the bottom half would be also half a meter. Okay. So now let's say that we were to pull this pulley all the way to the right here, so that the mass 1 is as far as you can go, right? This is the length of the string, right? And we know this is going to be 1 meter. Okay. So here's what I want you to think about, which is the pulley. How far did the pulley travel? So the pulley traveled 0.5 meters, right? The pulley traveled 0.5 meters. And M1, mass 1, traveled how far? 1 meter. 1 meter. So what this is telling us is that mass 2, for every meter that mass 2 travels, mass 1 will go double, right? So whatever distance M2 goes, M1 is going to go double the distance. Okay. So using our kinematic equation, delta x equals VIT plus 1 over 2 AT squared. Let's say the initial is 0, okay? And we're dragging at constant acceleration here. So that means if I double, right? If I double the distance that it moves in the same amount of time, the acceleration has to also double, okay? So I would say A1, the acceleration of mass 1 is going to be 2 times A2, which means 2 times 1.2, which gives us 2.4 meters per second squared. Now we're going to take a look at question 2. And in question 2, they want to know what is the tension in the string that is accelerating mass M1. So assuming mass M2 has this acceleration, and we know we calculated the acceleration of mass M1, what is the tension on this force to cause that acceleration? Now, there is also some friction here, so we got to take that into consideration. The first thing I'm going to do is to indicate my system boundary around the system of the object of interest and draw the force diagram. So the forces are going to be M1G. The ground is providing a normal force, which I'll call capital N. There is a tension force to the right, which I will call T, and then a smaller friction force towards the left, which I will call little f here. Okay. So we'll use Newton's second law. Net force equals ma, and the net force, I'm going to call this Fx here so we know it's horizontal direction. My coordinate axes are going to be positive to the right for the x and positive up for the y axis. The net force horizontally is going to be the tension force minus the friction equal to M1A. Now I'm looking for the tension force, so I'm going to substitute. I need to figure out, I don't know what friction is, I got to calculate that, so that's going to be mu n equal to M1A. N is equal to M1G because it's not accelerating vertically, so I can substitute that in. Mu M1G equals M1A. So then our tension is equal to M1A plus mu M1G. Okay. Now I'm going to do some substitution of numbers, and we'll do that right up here. So we have the tension force is equal to M1 is 8, the acceleration is 1.2 plus mu is 0.52, m1 is 8, and g is 9.8. Okay, so then we can calculate that, and we get that the tension force is 60 newtons. All right, so that is the amount of tension needed to accelerate this mass 2.4. Actually, this is 2.4. Sorry, that we calculated this in the first part, so this is 2.4. So 2.4 meters per second squared towards the right. Given that there is some friction there, this is the tension force needed to get that acceleration. All right, now we'll take a look at part 3. What is the magnitude of the force F required to accelerate the system at the given acceleration? So now we're trying to solve for F. And once again, we're going to draw our system boundary. So this is our object of interest. And we're going to draw our force diagram. So in our force diagram, we have m2g, our gravity force. We have our normal force. We have the force to the right, our applied force. We have two forces to the left, which are going to be the tension force from the string. And we're going to start with, oh, and also, we also have, out of space here, but we also have, make the circle a little bit bigger right here, okay? We also have friction, right? So we also have friction. So we have several forces here. So we're going to use our net force equals ma, net force equals ma, and then we're going to substitute all the forces in here, right? So we have the force to the right, and we're making right positive, like before, right positive and up positive. Okay, so we have F minus friction, and then there's two T's, so minus two T's equal to M to A. Okay. And we're solving for F. So let's isolate F. So F is equal to friction, and then if we move this over, right, friction will be positive, the two T's will be positive, plus M to A. Okay. And we know that friction is, kinetic friction is mu times the normal force. And the normal force, because these are an opposite, it's not accelerating up or down, we know that the normal force is equal to m2g. So this is going to be m2g plus 2t plus m2, and this one should be a2, right? That's a2, m2a, a2. Okay, so now we're going to substitute the numbers in here, and we get 0.52 for the coefficient of friction times mass 2, 12 kilograms, times 9.8. Okay, so that's the friction part, plus the tension part, 2 times 60, 60 from part 2 of the problem, plus M2 is 12 kilograms and has an acceleration of 1.2. Right. So if we calculate that, we get a force of 196 newtons.